everybody, what we're going to talk about today is deflection. So this is out of chapter 12 in the Hibbeler book. Let's write that down. So this is Hibbeler, and this problem's from the 10th edition. So it's 1235 if you happen to have that book. And what we're wanting to do is determine the equation of the elastic curve, and we're told EI is constant. Okay, so E is modulus of elasticity, I is just moment of inertia. So those are just, that product is constant. Okay, now in chapter 12, that is the deflection of beams and shafts chapter in the Hibbeler book. So there's several different methods it talks about for finding deflection and slope. Talks about elastic curve and all of that. What we're going to do is we're going to use the Macaulay functions to solve this problem. All right, so it is like the second method it kind of goes over in that textbook. So let's go ahead and get started. Now, first of all, what we need to do is figure out what's going on at A and B. Right, those are our external supports. I've got a pin here, I've got a rocker. So I need to figure out what is happening right there. So let's go ahead and just draw out a free body diagram, and then we'll see if we actually need to do equilibrium equations here. Okay, so we've got a couple moment right there, another one over here, and then we've got a pin at A. So let's just put AY. Technically we should draw an AX, but that's going to be 0 because that's the only thing in the X direction. We've got a rocker at B, so that's just a vertical force there. Let's call it BY. And then we've got this distributed load. So to get the resultant here for this one, we're just going to take the 3, multiply it by 8. That gives me 24 kip. All right. And then if we measure from over here, that would be located 4 feet to the right of A, so that would be a total of 8 feet there. Now, looking at this, it looks very symmetric, right? This is 4 feet, this is 8 feet, this is another 4 feet. We got these two moments. This is right in the center. So just looking at it, I can already tell that AY and BY will be the same thing. They are going to be 12 each, right? And you can go through and, we can show that. So let's just do one of the equations. Let's just do the moment equation about point A, just to show you that it is 12 in case you're not seeing it yet. Okay, so counterclockwise is positive. That means we're going to have a positive 5 here. And this is point A right here, right? So no moment created by AY because it goes through A. This one does create a moment. It's going to be negative because it's clockwise. And that'll be 24. Distance is basically from here to here. So that's 4. And then we've got BY. Whoops, I'm writing this in the wrong place, you guys. Let's put that down here. There we go. And then we've got BY. That's going to be a positive. Distance there will be 8 because we have this distance of 8 feet between A and B. And then finally we've got the 5 kip feet over here. That's clockwise, so that's going to be negative 5. Okay, and then we set it equal to 0. So solve that, and you get BY is 12, just like we said. Now it is symmetric, so that means AY is going to equal 12 also. And you could prove that by doing the sum of the forces in the Y direction if you wanted. Okay, so now we've got that. So what I'm going to do is I'm going to come over here and draw another free body diagram. And this time we're going to put those external forces on there. So here's our moment on that side. We got one over here. And then we've got our AY, which is 12. BY, which is 12. And then we've got the distributed load up here, and that's just a uniform distributed load, and it's 3 kip per feet or per foot. All right, so now I've got this. Now we're going to be using the Macaulay functions. Okay, now in the case where we've got a distributed load that's kind of in the middle, or it's over here, it's it's not starting out and going all the way across, right? It's not consistently across the beam. What we're going to do is we're going to extend this out to the end of the beam. All right, so let's use a different color to do that. And this is what we do with the Macaulay functions. Okay, so we extended this out. Now the problem is this isn't really here, right? We just put it there. So I need to take away the effect of that. So I'm going to come down here on the bottom and basically put the same thing but in the opposite direction. All right. So that way it cancels out. So now we've got this. All right, and you might be wondering why we need to do this. Well, it's because of the way the Macaulay functions are written. So if you have a textbook for mechanics and materials, you probably have a table that looks something similar to this. So this is obviously from the Hibbeler book. And basically if you look, these are the Macaulay functions. All right, so if we look over here at this distributed load, for instance, notice this is at the end of this beam, right? The way it's drawn. So here's X being defined. Here is A. A is the distance from the left side to the start of the distributed load. And then, you know, here are the Macaulay functions. So we're doing X minus A. So these are designed, basically these functions are designed to have the distributed load going all the way to the end. Okay? So what we have here, you know, this is just in the middle. So I need to extend it out so that I can use these functions. Okay, but now I need to take off the, you know, effect of this part we added. So we're going to go down here at the bottom, do it in the opposite direction. And that's why we're going to do that for this method. Okay, so we can use these functions that are in the table. Now, what we're going to do to get our moment equation, and the reason we want the moment equation is because we want to find the equation of the elastic curve here. All right, I can't even remember if I read this problem statement at the beginning, but that's what we're looking for. We want the equation of the elastic curve. So basically it wants to know an equation for V. So V is the symbol the Hibbeler book uses. I know a lot of people use Y, but this textbook uses V, so that's what we will use. All right, now in order to get V, we're going to use the equation EI times the second derivative of V with respect to X equals M. Okay, so I need to get M right here. M is for the moment. What we're going to do is we're going to use the Macaulay functions to get the moment M. So let's do that next, and then we'll go back to this equation and figure out how to get V. Okay, so let's go ahead, let's look at this table here. We're going to focus on this last column because these are the moment functions. All right, so let's just go from the left to the right and we'll go step by step. And let's write this right here. So right here we've got a moment, an applied moment, right? It's clockwise 5 kip feet. So if I look on this table, here is just an applied moment. All right, notice this is drawn as clockwise. We come over here. This is our equation. Okay, so we're going to put -5, right, because I'm going counterclockwise, which is the opposite direction of this. So we're going to have -5, and then we have X minus A. Now what would A be here? So A is the distance from the left to where the moment's applied. So for us, since we're applying this on the end, this is going to be 0 for A. And then we have a power of 0 here. Okay. So that gets that one. Now go to the right again. Now we've got this applied load, okay, 12 kip. Well, we look here at the table. Here's one with an applied load. Again, notice we've got X. Here's A. A is just the difference or the distance between the left side and where that force is applied. We're wanting the moment. So we're going to have the magnitude of the force, which is 12 for us. and then x minus a to the power of 1. Okay, so notice this is up, which is positive. That's what we have here. So we're going to have plus 12 x minus a. A for us is going to be 4, because the distance between the left side and 12 is 4. So put a 4 there. We have a power of 1 from right there. All right. Then moving along, we get to this distributed load. Now keep in mind, we've extended it all the way to the end now. Okay, so we're going to come over here and let's look at this. All right, this is a scenario we have. Okay, so if we have this uniform distributed load, this is our function for the moment. Notice this is going up, so it was positive. Ours is going down, right? So what should we do about that? We should make it negative. Okay, so we're going to have negative, and then we have our w over 2. So our w is 3, so we're going to have negative 3 over 2, and then we're going to have x minus a. A here is going to be 4, because the distributed load starts right here, which is 4 feet from the right, or from the left side, I should say. So x minus 4, exponent of 2. All right, takes care of that. And it's kind of hard to see here with my drawing, but we have another applied force here, that by, that 12. So we need to have that. So again, this one. So we're going to have 12 times x minus a to the power of 1. And this is going up, so it's positive. So we got 12, and then times x minus a. So what would a be? Well, I'm thinking it'll be 4 plus 8, which is 12. All right, it's raised to the power of 1 there. And then lastly, we come over here to this part we added on the bottom to cancel out this, right? So now distributed load, come down here. Same scenario, so we're just going to use this equation here, right? Our w is 3, and now we're going up, so it's going to be plus 3 over 2 x minus a, where a is the 4 plus the 8, so 12, right, to the power of 2 there. Okay, now I know you might be asking, well, what about this 5? Well, we can write it out just so you can see how it is, but we're not going to need it. And I'll tell you why in just a second. So this is an applied moment, clockwise, same direction we have. So we're just going to have 5 times x minus a. A here would be 4 plus 8 plus 4, so 16 to the power of 0. Okay, now this one we don't need. All right, and we don't need it because for our function, what we're doing is we're measuring x. Can we ever have an x beyond 16? If we look right here how x is defined, no, right? Because x is defined from here, and it would go to the end of the beam, which would be 16. So since we're never going to go beyond that, just get rid of that. So let's just say we don't need this one. All right, and that's because it's at the very end of the beam. We'll never need to use that. Okay, so just take that one off. So this is going to be our moment function. So now we're done with that table. And now what we're going to do is we're going to go through and we're going to figure out how to get v. So we're going to use this equation here. We have m. That's what we just found right here, those Macaulay functions. And I need to basically use this to somehow get v, where v is our deflection. All right, so let's write this out. So EI times that second derivative of v with respect to x is going to equal this very lengthy equation. So let's see if we can simplify anything. If you notice right here, I've got an exponent of 0. So anything to the power of 0 is what? 1, right? So that means we're just going to have a negative 5 here. Okay? And then can't simplify this next one, so that's just plus 12 times x minus 4. we got negative 1.5 x minus 4 squared plus 12 x minus 12 plus 1.5 x minus 12 squared. All right, so this is the equation we're working with. So now I want to work towards getting v. Now the way we're going to do that is we're going to integrate both sides. Okay, so we take the integral of this side, we're going to have ei dv dx, and then for this side we're going to have negative 5x. All right, so you're just doing an integral with respect to x here, plus 12, and then we're going to have over 2 times x minus 4 squared. All right, so again, you're just doing the integral here with respect to x. All right, next would be minus 1.5 over 3, right? Because this is squared, so we integrate, we get cubed. Put that 3 there in the denominator. Multiply by x minus 4 cubed. What would be next? This one. Exponent's 1 here, so when we integrate, we're going to have plus 12 over 2 x minus 12 squared. And then last term. This is squared, so when we integrate, we get 1.5 over 3 x minus 12 cubed. And then let us not forget, since we are integrating, we've got a constant, C1. Okay. Now, this still is not v, so I still need to go through, integrate one more time to get v. Okay, so left side now will be eiv. So that v is what we're looking for, and then we integrate this again with respect to x. So that gives me negative 5 over 2x squared plus, since this is 2, we're going to divide by 3. We'll have 2 over 6, right, because we have 2 over 12 times 3 there. And then x minus 4 cubed minus, notice this is cubed, so we integrate, we get 1.5 over, what is that, 3 times 4, so 12. X minus 4 to the 4th. This one's squared, so integrate, we get 12 over 2 times 3, which is 6, times x minus 12 cubed. And then we're almost done. This one's cubed already, so we're going to have 1.5 over 3, whoops, times 4, which is 12, times x minus 12 to the 4th, plus c1x, plus another constant, since we did just integrate again. Okay, so now we've got this, and let's just call that equation 1. Now, I've got two unknowns here, right? I've got C1, C2, so we have to figure out what those constants are. The way we're going to do that is by using boundary conditions, and these are pretty easy to find. So the easiest thing you can do is think about where you're not going to have deflection. Okay, that's the first thing I always do. And I need two sets of boundary conditions because I have two unknowns, right? So I need two sets of equations. Now, if we look here, I've got a support at A and a support at B. So can there be a deflection at those points? No, there cannot be, right? Because there's a support there. So that means we can say that V is 0. And let's find the x value. So x is measured from the left. So at A, x is going to be 4. And then over here at B, x is going to be 12. Okay, so V is 0 at x equals 4, and V is 0 at x equals 12. So the easiest thing to do is look for where the supports are. You know you're not going to have deflection at those points. All right. And that gives us what we need in this problem to solve. Some of the other problems you need to look at slope, but we don't need that in this problem. So what we're going to do is we're going to use these values in equation 1, and then that will allow us to get C1 and C2. Okay, so let's do that. So let's do the V equals 0 at x equals 4 first. All right, so left-hand side goes to 0 because we have EI times V, but B is 0. And then on the right side, everywhere we see X, we're going to plug in 4. So we get negative 5 over 2 times 4 squared. Okay. Now this next one, let's see what that's going to be. All right, because remember, these are Macaulay functions. So I just said everywhere you see X, plug in 4. That's not necessarily the case here because these are Macaulay functions. So let's look at this one. Okay, so we've got 12 over 6 times the X minus 4 over 3. Now, for the Macaulay functions, you got to remember there is like a set of conditions that we follow, right? And it tells us what to make this. So we're going to set this term here, this function, to 0 if X is less than A, right? And if X is greater than or equal to A, we're just going to do the calculation X minus A to the power of N. Okay. Whoops, that should be X greater than equal to A. Okay, so this is what we're going to use here when we're doing this part. All right, so X is 4, A is 4. All right, so if I look up here, what should we have? Well, we're still going to keep that, right? We're going to let X go to 4. And then notice you get 0 here. Okay. Now we come over to this one. Actually, we're at this one. So let's come over to this one next. 1.5 over 12. We've got the X minus 4. So before for our X is greater than or equal to A. So we just plug in 4 here. Raise it to the power 4. Obviously 4 minus 4 goes to 0 there. Now let's do the next one. So 12 over 6. Now on this one, 4, which is our X, is less than 12, right? Because A is 12 here. Okay, so because of that, this term is going to go to 0. And that's because X is less than A there. Okay, then this one is next. So 1.5 over 12. Again, we've got this X minus 12 to the 4th now. But A is 12, X is 4. So 4 is less than 12, right? So X is less than A, so we set that term to 0. Okay, and again, that's because X is less than A. And then finally we have this plus C1 times X, which is 4, plus C2. Okay, so we canceled out a lot of this stuff, which is good. All right, so we get 0 on the left side. This first term here is negative 40. Then we have plus 4C1 plus C2. Okay, I can't really solve anything there with that. I'm going to go ahead and rewrite it as 4C1 plus C2 equals 40. Call it equation 2. So now we need another equation. So now let's use the second set of conditions. So this is using equation 1 up here again. All right, but now X is going to be 12. So we're going to go through and do the same process. We're going to see if X is, less than A. If X is less than A in these functions, that whole function goes to 0. If it's not, we just plug in X equals 12. Okay, so left side's going to go to 0 again because V is 0. Whoops, I don't want to put that there. Now the right side, we got negative 5 over 2. Then we just have X squared, so it'll just be 12 squared. Plus 12 over 6. X is 12. 12 is obviously greater than A, which is 4, so we just plug in 12 here. So 12 minus 4 cubed. Then we're at this one, so negative 1.5 over 12. Again, we got x minus 4, so 12 is greater than 4, so just plug in the x equals 12, raise that to the power of 4, and then now we're over here. All right, so plus 12 over 6. X is equal to a in this case, so we're going to do 12 minus 12, power 3, but that obviously goes to 0. We're going to get the same thing with this one. All right, so 1.5 over 12. X is the same as a, because a is 12, x is 12. So just do 12 minus 12, which gives us 0. And then we're going to have plus C1 times 12, because we're plugging in x, and then plus C2. All right. So now let's go through simplify. Left side is 0. This term here is negative 360. This term right here, you do 12 over 6, which is 2, times 8 cubed. That is going to give us 1,024. This term here is negative 512. This is 0. The next one is 0, and then we get plus 12c1 plus c2. All right, so let's simplify all of that. So if we simplify it, I'm going to put the c terms on the left and then the constant on the right. And we end up with 12c1 plus c2 equals negative 152. Let's call that equation 3. Okay, we're almost there. So we've got these two equations now, and we have two unknowns, right? C1 and C2. So two equations, two unknowns, you solve simultaneously. So you can do it using matrices in the calculator, or you could solve, let's say this one for C2, plug that in here, and then get C1, and go that route. So we're going to take equation 2, solve simultaneously, however you want to do that. And if you get that done, you'll get C1 is negative 24, and then C2 is 136. Okay, so just do the algebra there. And then now that we finally have those constants, we had to do all that work just to get these constants. Now we can go back up to our equation 1, plug those constants in, and solve for v. And then that gives us our equation for the elastic curve. Okay, so from equation 1, we're going to divide through by EI. So v is going to be 1 over EI. And then basically we just write out this and include our new constants. Okay. And I'm going to simplify the fractions here. So we got 1 over EI times negative 2.5x squared. That's this first term. Plus 2x minus 4 cubed. And then this third term. This ends up being 1/8, I think. So we get negative 0.125. X minus 4 to the 4th. Plus 2. X minus 12 cubed. This is 1/8 again, so plus 0.125, x minus 12 to the 4th. And then we have plus C1x. So C1 is negative, right? So we're going to have negative 24x plus C2, which is 136. And then put a bracket. And that's it. All right. So there you have it. And just so you know, the term inside the bracket, the units for that would be kip feet cubed. All right. So that's units for what's inside the bracket. Whoops. Okay, so just so you got the units down there. All right, so now if these are the units, we have cubic feet. then over here, when you have your EI, when you cancel out the units, V will have units of length. All right, so in this case, it would be feet. Okay. And let's just say E would be KSI, and then I would be inches to the fourth. Convert this over, for instance, you know, you got to have the conversions in there so they're all in inches or feet. But when you multiply everything together, you will have units of length in there, either inches or feet, whichever one you go to. Okay, so hopefully that kind of walks through the Macaulay functions, and hopefully that made a little bit of sense. These problems aren't too bad. They get kind of long though, as y'all can see, because this is a 30-minute video here. A little longer than I anticipated, but that's what we got. Okay, so that gives you your equation for the elastic curve. And basically the elastic curve shows the deflection of the beam. So you could go through and basically plug in x values here and get the deflection at certain values of x along the beam. Okay, so there you have it. I will see you guys next time.